Okay. All right. Why don't we, is everyone, is it inside from outside? Let's start. Let's get started. Okay.
12:15.
Go to 12:15. Okay. So actually, let me ask that people close their laptops. I like to joke. I did that in my class last year after being annoyed at students looking at their phones. Let me tell you, if you're a student, your professor knows what you're doing if they see your eyes like this. But I had one kid who reluctantly put his phone away and then he fell right asleep. So I hope that doesn't happen to you. But I don't take it personally. Okay. Let me tell you a little about, this is a primer. So this is a very basic lesson in Fourier optics. Very basic, just to whet your appetite and to convince you that this is a subject that's actually worth knowing. I think actually any practicing astronomer, astrophysicist should know a modicum of Fourier optics. And so this is to whet your appetite. And along the way, we'll learn a little about the wavefront, and then in the exercise portion, and what I hope to do is just keep I only yap at you for about half an hour and then leave ample time to use some sample code from me and from Chris Davis. Chris, back there, has helped out enormously with this. So we've got some sample code and some information from the optical model of LSST that you could play with. And then I've got some general questions that you could go explore. So hopefully you'll have half an hour or 45 minutes to do some exploration with that. And I hope develop some intuition about optical wavefronts. That's the goal of it. Okay. So let's start. Okay, so this is the primer part, a primer on Fourier optics. First, let's start off, what does a telescope do? A telescope converts, I'm going to assume you don't know this, because actually I've been surprised to find how many people actually don't know this. A telescope converts angle on the sky to position on the focal plane. That's what a telescope does. Okay, so keep that in your head. Now we can idealize the telescope. We'll call it an ideal optical system, which takes an incoming plane wave. So a distant point object like a star is a superb plane wave, right? Because any wave of light is coming out spherically. It's so far away, of course, that spherical wavefront appears to us as a plane. And at the top of the atmosphere, that is an excellent approximation. Okay, now the atmosphere may screw that up. We'll hear about that some from Josh after lunch. But it's still a pretty good approximation. Now, what's the telescope? Let's idealize it in terms of two pupils. An entrance pupil, okay, so some hole where the light comes in, and an exit pupil, some hole where the light comes out. I think if you read an optics textbook carefully, they'll define what the pupil is more carefully than I'm going to bother to here. What a telescope does is it converts the incoming plane wave in the entrance pupil to an outgoing spherically converging wave. Okay? And so that's a wave that will come to a focus at our focal plane. And we can think about that as happening at the exit pupil. I will say for a lot of telescopes, the pupils are actually the same and very general. In a lot of telescope systems, the primary mirror is both the entrance and the exit pupil. And so that's simpler. That's not true with all instruments, of course. Okay, so with incoming plane wave, outgoing spherical wave, we have our focal plane. Now, you might notice, so we'll talk about two different planes. We'll talk about the exit pupil plane and the focal plane. And those are conjugate planes. And in a similar way, the angle on the sky and the position on the focal plane are conjugates, okay? And so I mention it in those terms as conjugates just to kind of give you the hint of Fourier transforms, which, as you should remember, is is a way of relating different conjugate variables. Okay? Now, I have a little animation, I forgot that. All right. Yes, angle. So there you go. That's really what happens. If the angle changes, the position changes. Oh, I forgot I had that. Okay. Now, I recommended in the resources this textbook, Goodman's Fourier Optics. That is an excellent book. I recommend it very, very highly to you. It goes through in a few chapters from a scalar version of electromagnetism to Fresnel and then Fraunhofer diffraction. Okay? So if you want the details of that derivation, Goodman's book really is the best source that I've seen. And so let's start with Fresnel diffraction, which how many of you have seen that in a course at some point? Everyone's seen it. Okay, so everyone's seen it. Good. All right, so here's the way we can write that down. That the image here is given by something that looks like a Fourier transform. Okay, so we're going, right, this is a Fourier transform. It's going from conjugate variables u and v to x and y. So u and v, pupil plane, focal plane, times some kind of complex phasor that, and we'll talk about what this pupil function is in a second, because that's where our wavefront is kept, times this phasor. And this piece is actually this piece represents the kind of spherical wavefronts you have in the Huygens principle. So you remember when you learned about diffraction, you might have learned about the Huygens principle, which said that at any wavefront, you could see how that wavefront moves by writing it as a whole infinite series of spherical wavefronts emanating from each part of the wave. And that those add up coherently to give you what happens in any system, from going from one point to any other point. Now, if it's just a plane wave with no obstructions, you could write that and you just go from one plane wave to another. If here's some example where you've got a barrier and you can see what the diffraction at that barrier does, or refraction, by this Huygens principle. In Fresnel diffraction, that's what this phasor is, okay? You see it's got the u squared plus v squared. That's the spherical part. Okay, now Z is your optical axis. Z is the optical axis, okay? So it only really shows up here, just as a normalization term, or here, actually. Now, it turns out we can make an approximation to Fresnel diffraction. And this equation is harder to work with. So it's very useful to make the next approximation, which is Fraunhofer diffraction. And that applies in the far field. And there's a condition that you can write down that indicates when that will be a good approximation for many situations. But it turns out that it's also a good approximation when you have a spherically converging beam. Okay, so in this case, when we're looking, in our case of a telescope, looking after the exit pupil, then the Fraunhofer diffraction formula becomes a good approximation. And it basically consists in getting rid of that phasor term. And the image is then just a Fourier transform, right? This is a Fourier transform of the pupil function. And then we square it to get the image. So if the other kind of textbook problem that you should have seen is what's the diffraction pattern from just an annulus, okay? And that's called the Airy function, and it looks like this, and it just comes from this equation, and the pupil function in this very simple case with a perfect wavefront, that pupil function is just 1 inside the hole and 0 outside. So it's just a circle, okay? And that's an integral you can do with special functions, and it comes out to be just the Airy function, all right? Now, If you've also wondered in the diffraction formula, there's a, if you want to know what's the minimum resolution that you can make for some diffractive source, there's this famous 1.22. Does people know where the 1.22 comes from? Okay. Okay, so it's the distance, I guess, to the from the peak to the minimum of the Airy function. All right, that's where that comes from. So it just comes from this formula. Okay, so at this point we have this is a pretty simple formula. Okay, and the key thing about it is that we can generalize the pupil function to deal with more sophisticated cases. And in fact, we can. The reason this is so interesting is we can take complicated real-life optics and characterize them with this pupil function and really understand what the optics is going to do for our image. So that's why this is so useful. Okay, so let's look at an example of that. Okay, so let's suppose we have an imperfect optical system. So I've drawn this sort of idealization the same way. It's a plane wave, entrance and exit pupils. But now, let's suppose that instead of having a perfect spherically converging wave, I have an imperfect one. And I can write my imperfection as, imagine this red line. So the black line is the perfect case, and the red line is the imperfect case. So let's look at that over here. And so I can write the deviation of the real wavefront compared to this perfect one as some function w. Okay, so I'll just wait to let that sink in. All right, so it's a function of u and v, so that's the plane of the exit pupil, where that's defined. So it's
dimensions of length?
So w has dimensions of length, yes. Yes, it does. You can see that actually in the, I'll get to the formula in a sec. Okay, just remember that it's defined on the pupil. You can think about it as being defined over the surface of the primary mirror. And often that's close. Now, LSST, we've got 3 mirrors, so, where it really is more complicated, but it's certainly, the pupil is an annulus like the primary mirror. Okay, so there's this function that tells you how far off the perfect case you are. So now let's look at our formula. So I've written out the pupil function. So before I called it script p. Now I'm calling it plain old p of u and v. So this first part is just the shape of the pupil. So this is meant to be either 0 or 1. Okay, so it's the shape of the hole. Okay, so here it's just a circle. Some LSST, really, it's an annulus. Okay, so that's the shape. And then there's this complex piece that's e to the I 2 pi wavefront over lambda. So as Pat asks, w has units of distance. And that gives you kind of this complex phase in our complex pupil function. And that's this imperfection. And then here's the Fourier transform part, right? xu plus yv. That's a Fourier transform, again, from pupil plane to focal plane.
Can I ask you a question about
yes.
physical about the system? So if I want to think about the f1.2 beam, say that's coming into the CCD, in some sense, if I want to think about the angles of those photons that are coming in, it's the tangent to the wavefronts there, right? So that sort of, those are points that come in. So what about,
you could think of it that way, yeah.
So what about in this aberrated case where the mirror's been screwed up and I'm working in this Fourier transform type way and I'm using Gaussian or something, and I want to reconstruct what is the angular distribution of the photons that are actually coming into the CCD. Is that possible? Yeah. The angles, the angles are just given as sort of the perpendiculars to these converging wavefronts. And in reality, in an idealized system, you would have some set of rays that filled a cone with a hole in it. But with aberrations, that cone is distorted. Okay? Yeah, but I mean, at the end, if all I have is an aberrated wavefront and it's expanded in terms of actual profile of the beam is. Is it possible? I mean, or is that only conceptually possible, but computationally something you would never?
I have to think about it. It should probably be possible. Yeah, it would probably be possible. Yeah.
Is the W function, the small deviation, definite? Is it changing with time? Does it average to be 0? Or?
Okay. So the question is, does W average to 0, or is it changing with time? So it definitely does not average to 0. Now, whether it's changing in time, that depends on the stability of your instrument. Okay. So W is, so in the way I've described it here, this W is a product of the design of the optics. Okay, so you cannot design an optical system where W is 0 over a wide field. You know, it might be that W is 0 or close to 0 on axis. Okay, down the axis of the telescope, or at the center of the focal plane. But once you move away from that, you know, it's impossible to make W 0 everywhere. It will be non-zero, and even worse, it will definitely, absolutely be different at different points on the focal plane or different angles on the sky. It will absolutely be field angle dependent. Yeah.
Will it iteratively be independent of wavelength? Is that realistic?
No. That's an answer to one of my questions, so you can hold on to that one. Okay. Okay. So now, any other questions? Yeah.
UV are in real space, is that right? And not frequencies?
So Andy's question, are U and V in space? Yes. Those are in the pupil space, but yes.
It's not like if I think about radio astronomy where UV are the frequencies, visibility.
These are, yeah, yeah, they're not in frequency space. They're not. But I mean, but you also have to look at the way that I've defined the Fourier transform. So I've got two normalizing distances in the denominator there. Okay. Any other questions?
So your previous script PUV could been complex,
Yeah.
and this PUV is real.
This one's real.
What's the magnitude of the previous, of the complex?
It's actually, okay.
No?
In most systems, this should just be, in telescopes like LSST, this is 0 or 1. Now, you could, if you have, if you apodize your instrument, then this could be less than 1. And apodizing, people know what apodizing is? No, we're all imagers. So in other contexts where you really care about diffraction, so if you're doing adaptive optics, where you're trying to get down, beat down the atmosphere and get down to the diffractive limit of your telescope, you might start really worrying about what the diffraction pattern looks like. And in that case, you might not want to have sharp edges. And if you don't want sharp edges, that means you might make this less than 1 radially. And that will then control the shape of your diffraction. But you would put that in here. Now in our case, we just want as much light as possible, so we have a clear aperture. Let's fill first and then.
As time goes on, the LSST mirror will get dusty. Do you change P or W?
I would change P, actually. Yeah, you could do it by changing P.
It looks like maybe W give me a phase difference of the incoming, so different position, the incoming photon or incoming electromagnetic wave.
Yeah,
They have different phases.
that's right.
That it will interfere with each other. Is it that W what it does?
Yeah, I mean, that's right. W defines how the interference changes for photons at different points on the pupil, basically. That's a way to think about it. Yeah.
This Fourier transform is basically mapping this, in some sense, time difference at the pupil to a spatial shift
Right.
in X and Y at the imager, right?
People often don't talk about it as a time difference. The way it is often referred to is an optical path difference. And if you've seen that phrase OPD, W is the OPD. Okay, optical path difference.
That's another way to say the phase difference.
It's a phase difference, but it is a phase difference.
But the result is a shift in X and Y at the actual imaging plane, right?
Well, it will shift a lot of things at the image plane, right? Okay, now I'm going to jump to the next point. And that is that a very convenient thing to do to W, right? W is just a function, is to expand it with Zernike polynomials. All right, so, and this is a very common choice in optics, and it's common because, so there's two things you can point to with Zernikes. One, the Zernikes are a complete set on the unit circle, and since we often have circular pupils, that's a good choice. Two, and probably even more important, is that the Zernike terms correspond one-to-one with the classical aberrations. Okay? So I've shown here the first, well, one is just constant, Zernike 1 is constant. I've shown here up to the first 11 Zernikes. And they're written in polar coordinates. So even though, don't get confused, U and V I wrote as Cartesian, but rho and theta polar, but it's polar in the pupil, and they're much easier to write in polar. You could write them in Cartesian, I guess, if you wanted. So let's look at them for a second. So the first two are tilt. So it's rho cos theta, rho sine theta. These aberrations merely tilt the pupil plane, and all they do is move the image around in X and Y. And actually, that one you can show analytically pretty easily. The next one is focus. And I should say the coefficients here are based on a normalization convention in a particular paper by a guy named Knoll from the 60s. And there's also counter terms. So that's just some normalization convention. So pay attention to the leading term, all right? Don't be distracted by that. So that's tilt. Next is focus. So that's rho squared. So rho is the radial dimension in polar coordinates. And if you can imagine, if you've got a deviation that's rho squared, you're going to change the radius of curvature, right? Radius of curvature is just a rho squared. So if you change the radius of curvature, you're just going to change the point where you focus. So that term is the focus aberration. Oh, let's try. Yeah. If we had a selection of them, they're probably all equally bad. Oh, there we go. All right. It's dangerous. That's what I like. Thank you. Much better. Okay. So does that make sense for focus? That if you change rho squared, you'll just change the focal point. Now after that, they're harder to see. Rho squared sine and cosine 2 theta, that's astigmatism. Many of you may have astigmatic eyes. That changes the size of the image in X and Y. Coma is rho cubed sine and cosine theta. That gives this weird chromatic tail that confused people back when they were searching for comets. Trefoil as a sine and cosine 3 theta. That makes images look like triangles. And spherical is the next order up. It's rho to the 4th. Okay, and that does something funny to sort of the size of the images. But those are the leading Zernike terms, and they all correspond to these leading aberrations. Okay, so next, all right, quiz question 1. This will only take about a minute. And I don't give you enough information, really, but these are simulated stars, and I use the code that I've given you to make these. So after I'm done talking, you can explore more. But I'd like you to see if you can identify, just do it on your whiteboards, what are these for of astigmatism, coma, trefoil, and spherical. So just write it down. Let's take 30 seconds, and we'll see how well you do. They're all one. All of them have only one. They all have a little defocus, because if you didn't have defocus, you wouldn't see anything. It's annular. It is annular, actually. It is annular. Yeah, you can see it. You can see the pupil. It's. It's a one wave, or two. It might be two. It's really big. These are really bad. These are terrible. Just terrible. And it's like a quarter wave out of focus, I think. Okay, take 15. How many people have their guesses? All right, I'll give you another minute. Another minute. Okay, 10 more seconds. Everyone have their guesses? What is the Jeopardy song? Do 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 do. Okay, all right. Okay, let's see. Let's see. How should we best do this?
Top right.
Okay, top right. Who thinks this one is astigmatism? Who thinks it's coma? Okay. Who thinks it's trefoil? Oh, trefoil, okay, or spherical. Okay, that is coma. That is coma. That is actually the... Now, I should say, these images have very good seeing. Maybe we'll see a few times this good seeing at LSST. I put in a bit of defocus, because otherwise you don't see much of anything. And there's an enormous amount of each one of these. I think I put in 2 waves. So these are just horrendous. Horrendous. Yeah, Phil?
Aaron, you said that trefoil makes things look like triangles.
It does. It does, but wait, you'll see. You'll see. Okay. All right. Okay. What about this one? Who thinks that's astigmatism? Okay, so we already said, we ruled out coma. Who thinks that's trefoil? A couple people. Who thinks it's spherical? Okay, actually you're right, that is spherical. Okay, now, all right, let's do this one. So all we have left is astigmatism and trefoil. So who thinks that's astigmatism? Okay, or trefoil? All right, that one is astigmatism, and actually, you got it. It does have an XY. This one is actually trefoil. It's hard to see the triangle. Actually, it is hard to see the triangle. It is. It is. Okay, so just by comparison, so I think you should know that LSST has sensors on the 4 corners that are placed out of focus. And those are in the corner rafts, and those are the wavefront sensors. There are also 8 sensors that are used for guiding in the 2 in each of the 4 corners. And those out-of-focus guys are designed to measure the wavefront with every science image. And actually, if you're a colleague of mine on dark energy survey, DECAM has a similar system. And just to give you a little insight into why is that a good idea to have sensors out of focus, I can show you that here. So here are those same images. There are actually 2 waves. This is horrendous, just terrible aberrations. We should have nothing like this anywhere on the LSST focal plane.
So when you say 2 waves, you mean that W is equal to 2 wavelengths?
Yes. 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 And, but here's what out-of-focus stars would look like with each one of those giant aberrations. So here's the nominal case. So it's out of focus, and out of focus, you see an image of it's the pupil. Out of focus, you actually see the pupil. Okay, and I've even had spiders in these simulations. You kind of see the spiders a little. So there's the shape of the pupil. If you have a big astigmatism, then you get this XY effect very, very clearly. Coma looks you got this crazy thing where the flux is all on one side, and the circle goes way out here, and the hole is sort of here. Trefoil gives you a beautiful triangle, out of focus. And then spherical does this kind of crazy thing to it. Okay, so it turns out it is much easier to see the aberrations out of focus because all the light isn't on top of each other. The aberrations are kind of spread out across the pupil. And this is why it's a great idea to look out of focus.
So is it a bigger effect out at the edge of the focal plane where the waveform features are, or a smaller?
The aberrations are worse on the edge, yes.
So the spider is the same as the diffraction spikes caused by the supporting rod to support the second mirror?
I'm sorry, say it again?
So the spiders is caused by the supporting rod of the second mirror?
Yes, yeah. And it holds the camera up too, yeah.
So will the out-of-focus images at the edge of the field actually be used to correct these aberrations real time?
Yes, absolutely.
By moving the mirrors?
So yeah, so for LSST, there'll be control in the active optic system of the hexapod that holds the camera, so the camera can be moved. The hexapod that controls the secondary mirror can be moved. And the actuators that support the primary tertiary mirror and the secondary mirror. And there'll be something like 19 or 22 degrees of freedom that will be controlled in real time.
But during exposures or between?
Between.
And this is all because of gravitational sagging, basically, or?
A lot of it is gravitational sag. Some of it is certainly going to be differential thermal expansion. Some of it may be random variations. Yeah.
How many cones will LSST use for TV?
So LSST is planning to use 22 Zernike terms to fit the out-of-focus stars. The demand is lower over at DECAM. I only go to 11 or 15, depending on my mood. Yeah.
So the Zernike is orthogonal?
Yes.
Does that matter in terms of, your telescope, your mirror is sitting on a couple of hundred points. Does a kind of a Zernike expansion, is that the best basis? Does it happen?
Okay, so Andy's question is the Zernike expansion the best for the mirror? It turns out that it's not the best for the mirror because it's better to do it in a more physical basis set for the mirror in bending modes, so-called bending modes. A lot of them are similar to Zernikes, but not all bending modes are contained in the Zernikes. So yeah, in practice, one wants to be careful to work in a more physical basis. I think for LSST, that's what will be done.
But you don't rely on orthogonality in any.
You don't. It depends on how you analyze your out-of-focus, how you do the wavefront retrieval. Some methods do work better if they're more orthogonal. And actually, the Zernikes are not orthogonal on the annulus. And nothing is orthogonal once you digitize, once you pixelate. It depends, but it's an algorithm dependent question. Josh had a question.
Just a technical point. When you describe the meaning of 2 lambda, that's the RMS of W, right?
That's actually the value of W.
But
That's the
it varies over the focal pupil plane, though.
No. Okay. It's It's A. It's the coefficient of the Zernike. That's what's 2 lambda.
Okay.
To be precise, it's that coefficient.
Does that? And then we have to know how disease.
Right. And so then, yeah, you can look at often when people who are optical engineers talk about wavefront, they very often talk about microns at the edge of the pupil, or microns on the pupil. And so then you have to look at what the usually they talk about this A too. It's the coefficient to the Zernike.
So aside from this physical mapping, would it be just as good to use Legendre polynomials? I sort of looked around in SciPy and I couldn't find this function.
Yeah, they don't. Sadly, they're not there. It depends on your context. People in adaptive optics sometimes just use Fourier modes. But you will see in the telescope business, a lot of people will use Zernikeys because of this connection to real aberrations. Okay, I'm going to move ahead a little bit faster. Okay, so this is what those look like with more typical seeing. They're smeared out. All right, this is actually my last slide, and then we'll have some exercises. Okay, so let's talk about the point spread function, right? This is the whole theoretical machinery for how a star, gets turned into some image. This is the effect of the optics on the PSF. And we could write, so here's the image or the PSF. We could write that in the following way to take into account some extra effects. Effect one is we could write our wavefront in time slices. So I call it W of I in time slices, where at each time slice it's the optics plus a wavefront from the atmosphere. And so that's what Josh will talk about in his lecture after lunch. And so the atmosphere is definitely playing a role. It would come in like this. Another effect, of course, is we have a detector, an imperfect detector, whose response will be convoluted with this optical piece. So we could write that convolution like that. Now, very often, you might approximate the effect of the atmosphere by taking it out of the wavefront and just saying it's a kernel that we could convolve with. Now, and so that might be an approximate way of writing our PSF. So this is a more exact, this is approximate. It's worth looking at what LSST, this is what our requirements are. So this is what the instrument is building to. Studies of the site indicate that the seeing piece should be 0.6 arcseconds full width, half max. On the camera, the CCDs have a requirement that the CCDs, and actually CCDs and all camera optical effects should be less than 0.3 arcseconds. And then the rest of the optics, so the telescope system, is about 0.25 in rough. These are rough numbers. And those sum in quadrature to about 0.7. And that's what our median delivered seeing is supposed to be. Now, there's more than just full width, of course. There's ellipticity, which is critical, right? If we're going to do lensing, we have to understand the ellipticity of our PSF. The ellipticity may come equally from these different sources. There may be sources of ellipticity in all these. My guess, I think our goal has been actually that the seeing dominate the optics. It might turn out those will be about the same. At dark energy camera, it turns out the optics are bigger, has a bigger effect on the ellipticity than the seeing, generally speaking. Okay, so here's quiz question 2. Let's take a couple minutes and do this. I've made a bunch of assumptions, even here, or certainly here. But even here, I've got some assumptions. How many violations of those assumptions can you list? Think about that for a minute or two. See if you can come up with several ways that even this expression does not capture our instrument. Okay. As you can write, let's write those down.
Is the window on the camera considered part of the optics?
Absolutely. It's optical, so it's part of the system. Oh yeah, you can't, if you didn't have it, it's part of the, it would be totally off. Yes.
But actually, that reading, which was excellent, they sort of did this run out for, and then the first one they said that you had to be far away, but then if you put a lens in, you get the same result. So you don't need to be far away.
That's the spherically converging. That's the spherically converging thing cancels the phasor, the Huygens phasor.
Does it cancel it exactly?
Pretty well.
This is the same as if you had the whole Fresnel-Kirchhoff
That I'm not 100% sure. But I think the Fresnel piece, I think it does cancel that out.
That reading was excellent.
Yeah. I think Josh found that.
And so, Josh, the PSF.
Okay. Do people have some violations, some things that are assumed? Does everyone have a couple?
Yeah.
Take 30 more seconds. I'll do what Andy did. We'll have people hold up your boards. Hold up your boards. Yeah. Pardon?
Why is the sum over T of I and not I? What is T?
Oh, that's just it's a sum over I.
Okay.
It just means different time chunks.
I see.
That's all.
Okay.
Just different time chunks. Okay, sorry. Bad notation.
Yeah, I'd like to understand CCD better.
I would too.
Okay, all right, people want to hold up their boards? Hold up those boards if people have things written down? Yeah, don't be shy. Don't be shy. Okay, only one person has their board up. Come on. Come on. I know they do. Okay. So who in the back? Who's being blocked? What do you have? What's on your board?
The first one is the so-called brighter and fatter effects that we discussed from the last 30 years.
Okay, so does everyone know what the brighter fatter effect is? I see some. Okay. Some people in the room have been working on it for the last couple of years. Craig has. Andre has done a lot of work on it. This is an effect discovered where as more charge is being deposited in the CCD, the charge sees the lump of previous charge, and it bends away from it. And that changes the shape of the response in a way that violates this convolution. Okay, so yes, that's a good one. What was the second one you had?
The so-called charge transfer efficiency.
Do people want to know what charge transfer efficiency or inefficiency is? Okay, I see a lot of shaking heads no. That's an effect inside CCDs where CCDs are a bucket brigade. The charge is passed from one pixel and then across. And it doesn't all go. Some of it gets stuck. If there are traps in the CCD, some of it might get stuck and not transferred till the next time. That, depending on how it happens, could violate the convolution. In some cases, it doesn't violate the convolution. It just means that this function that you convolve by is different everywhere on the CCD. Okay? Okay, those are two good ones. Who's got more? How about you?
There was some wavelength dependency of
Chromatic.
Okay, so wavelength dependence. Seth mentioned that. That's right. The wave front could be wavelength. In fact, it is wavelength dependent. Even that varies with wavelength, and this can vary with wavelength too. Okay, what do you have next?
there was the optics and atmosphere might not be a simple sum. That might be across the...
That is actually a pretty good approximation. That's good. That one is good. I think that one is actually quite good.
What about the bit of the atmosphere that's inside the optics?
That is actually not zero, and that one is evil. So that you can count that too. Count that too.
Even if W is the sum of optics and atmosphere, is it still legitimate to assume that you can write them as a convolution?
So this, not necessarily. Yeah, this approximation might not be perfect. I think in a lot of cases it is actually quite good, but definitely not perfect.
How much of the assumption of your initial calculation, though, is that the original thing coming into the pupil was a plane wave? Which
Well,
would be true, of course, if the atmosphere is already screwed up.
No, but that's what the atmosphere is doing. It assumes it's not this is the piece that's not a plane wave coming in, and that this then will apply. Oh, yeah. I'm sorry? Okay, so Stewart's is what if the camera is shaking or the telescope is shaking a little bit? And that does happen. You know, if it's windy, it could shake a lot. That actually comes in. You could put that in here. You could treat it the same. You could just lump it in there. So at least the form of this would still hold, actually. Yeah, Jim.
It's not clear if this is wrong or if it's just missing, but there's no spatial variation in PSF here.
Right. I just didn't write it. So, but it's a great point. It's an excellent point because, so Jim's question, what about spatial variation? Both W and the CCD piece are different spatially. And W especially. It also varies in the focal plane or in the angle on the sky. It absolutely does vary. It is not a constant across the field of view. That's definitely true.
Would you normally parameterize that in angle on the sky or in focal plane units? Is there a reason to choose one or the other there?
Well, those are the same. Well, let's see. So the question, yeah, they're slightly different depending on the distortions. That is an area, that is a question of active interest. In some of the work that Chris and I have been doing, we've been doing it in the focal plane. But yeah, the distortion piece is actually not, that's actually something that's not here. There is another kind of deviation of light which is called distortion, and that's where your mapping is not rectilinear of angle to pixel. Okay, and so that's, I'm sure everyone knows about world coordinate systems. World coordinate systems take out the linear piece of that, linear distortions, locally. And then if there are worse effects, you know, that's another, you know, if something's nonlinear, then that's even worse. Yeah, Craig.
Is the fact that the atmosphere is changing with time, is that a problem as long as you can write it as a convolution?
Well, so yeah, I mean, the atmosphere obviously is changing with time rapidly. So this formally is still true. You know, I think you can, yeah, well, that's the approximation made here, that you can just put it in the compass. I think it is a pretty good approximation in most cases. Okay,
So
more.
your earlier point about position dependence, then just to be clear, XY there means kind of little local XY.
It meant
for
little local,
PSF,
yes.
For rays coming in that are all parallel at a particular angle.
Yes,
And then if you
yes.
have another angle, then that's.
It's a different W.
The global XY.
That's right, that's right. Okay, why don't we, all right, good. I think this was good. I think people came up with the things that I thought about as being violations. Let's use our remaining time in the following way. If people downloaded these routines and the Python notebook, okay. Okay, so the instructions are on the website. There's some code. So some of the code is it's an old version of the code that I use for out-of-focus star fitting for DECAM. Chris wrote code that does adaptive moments. It's the HSM algorithm that he coded up. And then I've got some data files that come from running the Zmax model of LSST. And that gives wavefront as a function of angles on the sky. Okay? And I've got a nominal one, and I've got some misaligned ones. Those are very badly misaligned. So you could do a few different things with that. Okay? One thing you could do that you might find interesting is to use that code to explore the functional dependence of PSF ellipticity on the wavefront aberrations. So the ellipticity can be written actually as a fairly simple function of, oh, I guess I should have written A of I. This means the coefficients of the Zernicke's. It's actually a pretty simple semi-simple function. And you could kind of explore it numerically if you like, just by putting in different aberrations and using that moment evaluation code to measure the ellipticity. All right, look at the x squared, y squared, and xy moments, and see if you can find a functional dependence. Okay, that would be one thing you could do. That's not too hard. So the idea is pick one of these. You're not going to be able to do more than one. Just pick one. Another thing you could do is use the pickles of the wavefront, and I have an example of of what's in that pickle in the notebook, to calculate the PSF ellipticity versus the focal plane position. Maybe you could make a beautiful plot looking at the whole focal plane and look at what the ellipticity is, maybe with a quiver plot. That might be nifty. And if you're more theoretically minded, it is possible to derive the functional dependence of the moments on the aberrations. You can actually derive this expression. And then maybe you could think of something else you want to try. Okay, so it's been half an hour. I'll roam around, see if I can answer questions, and see if you can make one interesting looking plot doing one of these things.
Maybe Chris, you could maybe roam around too.
Okay, excellent. Good. All right. And definitely, if people have trouble dealing with getting the code to run or the notebook to run, let me know. I have to thank Richard, actually. Richard tried running it yesterday, and it would have totally failed, except that Richard found all the problems. So thank you.
So the FFTW3 thing I noticed disappeared at some point from your instructions.
Yeah, that was the problem. It was too hard to install.
Okay, so this code now just doesn't use...
It just uses SciPy. SciPy, yeah. SciPy FFTs. They're just as good, just a little slower.
Okay, so...
Problems downloading code.
Oh.
We're working on it.
Oh, you have to be logged. Yeah, you have to be logged into Confluence.
No, I was logged in on this browser.
Oh crap! Then it's the numbering. I'm sorry. Yeah. Okay. Okay. So, I think in my little example, I call them by this number here, but the array starts at 0, so they're off by 1. Yeah.
So, given that some of them lived in here burn fat and different things, I think some of the students, it might not be clear why an out-of-focus image is a donut.
Oh, yeah. Oh, I'm sure that's right. Yeah. Yeah. Just looking at that. That's right.
Yeah.
That's right.
It's a cone of light.
Yeah.
And then
Yeah.
it comes and makes a donut.
Yeah. No, that's.
Sketch something on the board and poke it up.
Well,
But anyway.
maybe I'll just let them chew on this.
What was 2 and 3 again? Why do you set these to 0 always for this example?
Oh, because so 2 and 3 are the tilt. So I don't care where that will move the star around inside the grid.
It won't change shapes.
No, it just will move it around inside the grid. Okay. All right, I'm going to go back to the exercises. I mean, if people have the notebook running, I think it's easy to just change the values of the Zernike coefficients and just make some, and there's the little image already made, put in some wacky values and see what you get. Yeah. Okay, let me see if I can. Hey guys, can I scoot through? Thanks. Oh. I don't think I'm that skinny. I'm not that skinny. Sorry, thanks. Okay. Pardon?
For different reasons, neither of us can get things.
Oh, okay. So you have to do.
I did run that
You did
Python
the
command first.
and is. Yeah, that one. Yeah, and did that run?
It thinks everything is fine.
And are you working? You have to work in this area.
In that directory. This notebook is in that directory.
So try.
But
Oh crap!
it doesn't like it.
It's in that directory. You sure?
Yeah. It's a wave to image. That's what this guy is.
Yeah. Crud nuggets. Maybe Chris knows. Where'd Chris go?
You might want to ask people to raise their hands if they have everything working.
Yeah. So how many people, are other people having trouble with the Python line not working for them? Or have people got that working? I think people, so.
I have Python installed.
Yeah, no, it would fail. It would fail. Why don't you restart? Why don't you just restart your kernel? Restart your kernel. That's a good.
Oh.
Well, it's got the star.
It's still going. Oh, different problems.
Okay, that's. Okay, so that's good so far. Oh, what crap? How do you? Okay, so that's closer.
Yeah.
Try it was the wrong size. Crap. Okay, so that's Chris's code. I wonder how is this Python 3 or 2?
2.
Is it recent or some ancient version?
2.7.
Okay.
Standard one.
Okay, so hey Chris. Oh. All right. This is Chris's code is failing us.
I see some people have something working. So.
Yeah. The numpy.d type is the wrong size. Try recompiling. Try. No. All right, let's try starting the kernel again. I don't think that should. It shouldn't. It shouldn't. I've not seen that error before. Yeah. Hey, Chris. He's getting a bug in your just importing your code. It says it's got numpy.dtype has wrong size. Try recompiling. You ever seen that one before?
I've never
Yeah.
seen that one before.
Oh, I've just assumed people knew it, but maybe people don't know it. Yeah. Okay. Phil's going to help out by writing down the formulas to go from moments to ellipticity.
And they might be wrong, so weak lensing people.
Yeah. Oh, I guess I do have them in the notebook. Yeah.
When it compiled, when you did the setup, did you, no errors. Here's a question. Are you like 32-bit only? Do you know? Do you know what that means?
Oh, if you're 32-bit only, then you're. If that were true, how could that happen? Oh, then none of the code will work if that were true.
I forgot that one thing.
It's the name of the variable in the code.
Okay.
But it is x squared. It's the x squared moment.
All right.
Yeah, it is the x squared moment.
Yeah, in the code it's pi 1.
It's nice to write that E1 equal to pi 1. So C knows you.
Oh yeah. So all I'm doing here is just changing the. I'm just changing the things to 32-bit. See if that. Maybe it will.
Yeah.
I got, I get import Zernike and it didn't show up. So did I just fail to?
No. So if you have the directory and you untarred the tar file, you need to, your like Python path needs to know that that thing exists.
Either that or you have to work in that
So
area.
an easy way to do is to import sys.path.append to the directory
Or,
where those files are contained.
I guess I was assuming that you,
I
yeah.
thought it got installed when I did that.
No.
Okay.
So if, I might not have been explicit that this code is not being installed anywhere. So you have to work in the same directory that you download the code in.
I think you might have,
And then if you just do your Jupyter notebook from that area, it'll just work too.
Okay. How many of these files does it need? Just Zernike.py or all this?
It needs all of them. It needs all of them.
So if I just put that in the same place where the notebook is?
Yes.
I can move
Yes. Just put all the code where the notebook is.
I can do that.
Yeah, that's the easiest thing to do.
Problem solved.
Oh, what was the answer?
The answer is my computer is too old.
Oh, seriously? Oh my God. Okay, but it worked.
Yeah, so changing it in the code to use 32-bit.
Oh, wow. Chris is smart. Okay. How's it going?
I mean, I was just trying to vary these coefficients and see how the ellipticity varies.
Okay.
Yeah, this is maybe it's not the best
Oh.
way to do it.
It's not super fast.
Yeah.
So if you do 100,
Yeah,
it'll take a couple minutes. It'll work in a couple minutes. All right, I'm going to switch out again here. Thanks. Here. No, I'm good. Oh, look at that one. Yeah, horrendous.
Thank you.
Yeah. Fortunately, we'll never get anything quite the bad. Maybe the first image. It's bad. Oh, and I see Richard made donuts. Yeah.
Okay.
Yeah.
So huge Z4.
Yeah, exactly. So the relation between how out of focus you are, the size of the donut, and that is simple analytic expression. Just it goes as 1/8f squared.
So I haven't looked at the pickles, but there's a wavefront.
Yeah.
So that's a 2D array, is it?
The wavefront, it's 3D. It's got x index on the focal plane, y index on the focal plane, and then the Zernike array at each of those points.
Zernike array. So the
Zernike coefficients, yes. It's got Zernike coefficients at many places at a grid on the focal plane.
So it allows you to realize a model of the PSF at that point on the focal plane.
Exactly. Yes.
So going back to your plots, if I'm looking at different positions, so you say W depends on the position of the source in the focal plane.
Yeah. Yes.
So the aperture integral stays constant.
Yes.
It's just the perturbations that change.
That's right.
So that's why if I'm moving around and looking at different sources on the focal plane, that means that's why I have to do a different Fourier transform every time if I'm calculating the wavefront.
If you're using the wavefront to calculate the image.
Yeah.
Yes.
Okay.
Yes.
And the coherence of that is an open question about how many times I would have to sample.
No, but wait, are we talking about sampling the pupil plane or across the focal plane?
The focal plane.
So those are not, but are you talking about different, are you talking about an image at one spot in the focal plane or comparing this, one spot in the focal plane and some other spot in the focal plane?
I'm talking about looking at the point spread functions that move around.
Yeah, well there's no real coherence. I mean, there's only coherence at one spot in the focal plane at a time. There's coherence across the pupil, but not across the focal plane.
But there is some coherence, I would have thought, because I can measure point spread functions and interpolate what the point spread function is somewhere else in the focal plane.
Oh, that's just that the changes in, I'm talking about coherence in the quantum mechanical or wave sense.
Okay, sure.
But it's smooth.
Right.
The optical piece is usually smooth. So that's why you can interpolate across the focal plane. But that's just a question of, that's just how the wavefront varies depending on where you are.
But does that mean that the wavefront varies smoothly across?
It's usually pretty smooth. Yeah. It's usually pretty smooth.
Okay.
Yeah. Depends. Yeah. Because it's usually smooth because the beam, so the size of the pupil, right? The primary covers the whole primary. It's the beam size, and in most of the optics, the beam is big, so it's hard to get any you know, fast gradations.
Okay.
Yeah, yeah.
1616 is 0.
Yeah.
This is an error that you can help me with, but I just upgraded to the most recent SciPy, and
Okay.
I'm getting this horrific error. libg Fortran G4tran 1.4 not found.
Oh, that is not. That is not. Oh, you're having problems getting factorial.
Yeah.
Okay.
Right, which I should
That
have.
that I don't know.
Yeah.
That I think is now. If you can't import factorial, you know, unless factorial moved somewhere. I mean, yeah, you could Google where factorial is, and if it's moved, it's used inside the Zernike code.
Right.
So, if it moved, you can just change that one line. Find out where it is and change that line.
Okay.
Do people have any interesting plots? We've got. I think we have 15 minutes left, so you can keep beating at it. But I'd like to see. I hope people can make some interesting plots.
So if we look here at the center,
Right in the middle.
the focal 1616, the focal
On the
point
optical
is negative. Does that mean is this the point? The fact that it's focusing inside the CCD? Is that what that is?
It just means there is a little bit of, basically a little bit inside. Yeah. Well. No. So this is at the optimal focus for the whole array.
Yeah.
But the Z4 just isn't 0, okay? You know, because all the aberrations are combining in some way. And so it is not necessarily the case that the spot of best focus has Z4 of 0.
And this has nothing to do with the CCD.
No CCDs here at all.
Oh, so there is some optimal point which might have been inside the CCD, and this is just telling me that at that point in the center, it's not actually what we would optimally want it to be. There is some aberration which is left.
There are some aberrations. There's absolutely some aberrations, and there is some Z4. But it's not true that best focus has Z4 0. That just isn't true.
I see.
Even if the CCDs were infinitely thin and could just.
Yeah, this is not. There's no CCD here at all. This is just optics.
Because you want it optimized for the.
It's optimized over the whole focal plane.
Yeah, not just optical axis.
Yeah, that's right.
Okay.
So this is 32 by 32.
Let's see what else you think.
Yeah.
So for each one of these points, we can calculate a star and calculate the ellipticity of it.
Yep.
Can we set the noise to 0?
Yeah, if you want, sure, go ahead. Yeah, you could set. That's why I wrote the code that way. You could set it to 0. You could make it horrible. You could do whatever you want. Yeah, sure.
That part, figure out how to do it for one. So we want to.
Yeah. 10 minutes. Okay. Let's just take a couple more minutes, and then we could talk about some of the results. And while you do that, I'm going to get some of mine up. My results up here. Let's see. Okay. Yeah. Okay, so let's just call it one more minute maybe, so we have some time to talk about results.
Several times you said, and somebody also asked the question, you said that the PSF changes on the focal plane, which is true, but if you describe it in the UV plane or the Fourier domain, if the system is linear, then you have the same W of UV, I mean the same in the UV plane, but that will give you different PSF at different position. But you said that
Well,
in
also the
addition-
W is different. The W function, if you look, if you're on axis in a telescope, you have one W, and if you go off axis, you have another W. It's different, totally different.
Because, I mean, if the system is, the optic is linear, I mean, in the sense that it can be described by a response in the Fourier, I mean.
Yeah,
Fourier
but it's
plane.
just, I'm not sure what you're inferring from linearity, but there isn't one W for all positions. Yeah, there just isn't. Yeah, yeah. It's in fact, it's much, much different. Okay, I think, so we have about 10 minutes left, and I think it'd be useful just to talk about some of what we learned. So does anyone have an interesting plot they want to describe?
Not yet. It's running.
Not yet. People, it's running.
It's running.
Okay.
That can't be right.
Oh. What did you try to plot?
I tried to plot Chi1 and Chi2 versus Z5.
Versus, okay. So Josh tried to plot Chi1 and Chi2 versus Z5. That's good. But he got a straight line. So what?
Yeah.
Okay.
Independent.
It's straight. All right. Okay, that's good. That's right. I think that's right. Okay. Anyone else make an interesting plot? Craig.
I did the same kind of thing, and the only thing that really seemed to have a strong dependence was Z7, Jacobi. And it had strong dependence. The ellipticity had strong dependence.
Okay, so ellipticity depended on coma. That's good. Z8 is the other. The two comas, you know, they're just rotated on the pupil. Okay, so I'll show you the plot I made to do that. Let's see. Okay, so here's a plot. Let's see. Oh, I didn't label it. Sorry, I'm sloppy. So this is astigmatism versus, so this is astigmatism here in waves, and this is one of the, I think it's Chi1. And the reason Josh got a straight line, and I got this nice linear, nice line with a real slope, is I put a little defocus in. Okay, so this was one of the, when I said you could look for the functional form, one of the biggest terms for ellipticity is defocus times astigmatism. And there are two ellipticities, and there are two astigmatisms, and those map onto each other. One, I forget which, well, we could just see which one I did. Let's see. So I put in Z6, and I made a plot of Chi1. So Z6 gives you Chi1, and Z5 gives you Chi2. And I put in a little bit of Z4. And if I'd put 0 here, I'd get, well, we could just do it since it's a notebook. Wow. Awesome. I love this thing. This is great. Maybe? Oh, I'm not connected. Oh, well, hell with it. Okay, sorry. That's too hard then. Okay, sorry about that. Thanks, Chris. Okay. Anyone make any other interesting plots? Jim, what do you have, Jim?
Nothing yet.
Okay, he's trying. Did people take a look at the pickle of Zmax data? So maybe you just sort of ran through it. So people were asking me, you know, how is W different at different places? So that's what that pickle has. That's a real. I have the Zmax model of LSST. I ran that. Actually, a graduate student that was working with me last year, JB, actually did that study, and it's just run at a bunch of points on the focal plane. There's the things that are masked are off the focal plane, and so you could look at all those points and look what the ellipticity, look what the stars look like at different points in the focal plane. So maybe it's too much for half an hour, I think, to do that. But I'll just show you. So I use this nominal one. So that's the perfect system. No, that's if the objects were made perfectly, it's all aligned perfectly. That will not quite be the case. So I looped over all those points, and I made a star with all those values, and I calculated chi1 and chi2, and I ran the moment evaluator. And it takes, I did some printout, and I didn't do every one because it took too long. I did every fourth one to make it go a little faster. And then I made a quiver plot. People know about quiver plots. And then you gotta fool around to get rid of the arrows because you don't want arrows in ellipticity, right? It's not a vector, it's a pseudovector. And then I got this. Look at that. So that is what the ellipticity would look like across the focal plane for perfect LSST, no atmosphere. And here's 0.01. So these are really, really good. This looks just great, fantastic. And you could try running with the misalignments. Those misalignments are horrendous. And you'll see this will change a lot. So I will say you could also play around with different combinations. So coma, if you make stars, the coma will certainly affect the ellipticity sum. And spherical will affect it as well. And then if you really want to go wild and you want to look at third moments, this code has third moments. And actually, coma and trefoil will affect the third moment. And if you play around with that enough, you might discover why third moments are so hard, actually. Okay. So there's a reason flexion is not widely used in our community. Boov. Where's Boov? Okay, Boov's not in the room. Anyway, Boov likes flexions, but they're tough. Anyone else have anything they want to, ask or comment?
I just had a question about where those Z parameters came from the Zmax, all these pickles.
So if people don't know, Zmax it's actually a commercial optical modeling code. You give it your optical surfaces. So it just is it's a simple deck that has for each optical element, it has the shape of that optical surface, its radius of curvature, if it has an asphere, what the aspheric departure is, and the spacings. And the modeler takes a perfect incoming plane wave and traces rays through all the elements until you get to the focal plane. And along the way, it keeps track of the optical path distance for different points on the pupil. And from that, it makes the W function. And it will spit out the array of W's for the point on the focal plane you want, for the wavelength you want, given your optical model. And that's what I did. I mean, that's what we did here. We just ran that at different points in the field of view or different points in the focal plane and got those W's.
So it gives you the Zermke coefficients from Zmax.
Yes. Yeah. And so that's what those dumps are. So it's done at many points. And but it's in a form I hope maybe you can, you could play with it a little bit. I will say, if I think people probably don't have much intuition about optical quality, this is superb. So this size ellipticity, right, this is 0.01. Some of these are 0.0 a couple on the outside. But this is really excellent performance. Yeah?
Why isn't it circularly symmetrical?
Why isn't it circularly symmetrical? That's an excellent question, Phil. That is an excellent question. I have to think about it. I'm not sure.
Is there a 45-degree rotation that fixes that?
But it's absolutely true. The system itself is axially symmetric.
Is it a difference in ellipticity phase and position angle? There's a factor of 2.
Yeah, 'cause is this the physical orientation, or this is in that space?
This is in the focal plane. This is. I'm actually. I have to think about. Chris, do you know?
Yeah.
Oh, this is the ellipticity vector.
Take all the ones that are like this way.
Yes.
Find
Yeah.
angles like that, and I think you end up with something that looks.
Yes. Yes. I bet that's right. I bet that's right. I'm always happy when I learn things from my grad students. They're smarter than me. That's great. Thank you, Chris.
They're half our
Yes.
age.
What?
They're half our age.
No, twice as smart. So, yeah, I think that's right. That's right. Yeah.
But the amplitudes are right. It's still 1%.
Yeah. Yeah. The amplitude should be right. Does anyone have any other? I think we're about on time. Anyone have any other questions or comments? I'm happy to discuss as the week progresses if people are interested.
Okay, so let's first thank Aaron for the